All right, can you hear me? All right. Okay.
Yes.
But very much like our last speaker, what I have to talk to you about today really has two parts. Our core technology at Core Computing is really around building quantum computers, quantum processing units, built with very good qubits. These are neutral atom qubits, rubidium atoms, whose electronic states are really used to manipulate quantum information. And we use PICs, integrated photonics tricks, mostly for the control of these neutral atom qubits. So our core product is really the neutral atom quantum computer. And you can see a version of that quantum computer up in the right-hand corner of the screen right now. Each one of those dots that you see in that picture is a neutral atom qubit that we use. That's a single atom that's scattering about 1,000 photons each into a CCD camera. And that's what we're using to read out the states and the location of the qubits in our quantum computer. So I'm going to tell you about both of these things today. But first, just to give you a sense of the company, Quantum Computing, very much like New Quantum, we started in about 2019 and we spun out of university research. In our case, predominantly research labs at Harvard and MIT, in the research groups of Misha Lukin, Marcus Greiner, Vladan Vuletic, and Dirk England. We've grown since that time. This slide is actually a little bit out of date. We're now well past 80 scientists and engineers. We're up to about 100 people or so. And it really is a family, more than a team. But the technology that we work on really started around 2015. We started the company in 2018 to spin out and commercialize that technology built on neutral atom quantum computers. And we've really had two kind of non-incremental breakthroughs in how we view this technology. One was just being able to produce large arrays, large for the time, of 50 qubits or so in 2017 and really manipulate them with high gate fidelities and be able to show that neutral atoms as a qubit really were starting to come into their own. But just a few years later, we actually discovered a new technique in this technology, which is that we can actually shuttle atoms around in real time and in real space. And I'll show you in just a moment how we do this using optical tweezers to manipulate the atoms and still preserve their quantum coherence. So that allows us to make processors where we can really get all-to-all connectivity, bring any two qubits in the processor together and implement a relatively fast Rydberg mediated gate. So this is the technology that we're working on. These are the types of processors that we're building here. And I'm just going to give you a good sense of what the processors look like in a single slide here. What we actually do is shown in the upper left-hand corner of the screen. What we do is move the atoms around in real time. We use the internal electronic states, both the hyperfine levels of an atom and also the excited Rydberg states of an atom to implement single and two qubit gates respectively. And actually, I wanted to show you a good sense of how we do this in real time. In the bottom right-hand corner is a video of actual single qubits that we're moving around, shuttling in an experiment. And every time you see two get close together and circled by a red circle there, what we're doing is implementing a two qubit gate using the Rydberg entanglement that we can generate by exciting the atoms all the way up into the excited state spectrum so that they interact at a distance, but not too long of a distance. And that way we can implement these kind of localized gates. So what you're seeing in the movie there is actually implementing a toric code on a torus, so we can actually use this to do things like error correction as well. But we do very well with these kinds of qubits. We get single qubit fidelities that are in 3 and 4 nines, and we can even get two qubit gate fidelities that are 99.5 or so in the state-of-the-art experiments that we're doing now. But I should say that, this moving atom architecture really allows us to make optimized kind of zone architectures where we are really doing all of the basic elements of operation of a quantum computer in an optimized kind of geometric sense, which is to say that we have regions that are devoted to memory for qubits. We have regions that are devoted just to entangling them, but we also have specialized readout zones where we're moving the atoms down spatially, removed from the rest of the atoms, so that we can scatter photons out on them and not destroy the quantum information that we have in the rest of the processor. So this is a very powerful type of system, but to really reach the utility scale, we do have to scale them quite a bit larger. And as we scale up a quantum computer, we also have to scale up the control. So that can be a very difficult problem. Once you get up to the point that you have, say, 1 million qubits in your quantum computer, we're pretty far from this now, but we're starting to invent the tooling for this. And this is where the PICs come in. So the real question is, how can we implement these types of systems with very high clock speeds, moving the atoms a little bit less because that's somewhat slow operation, And all of those roads lead to scaling up the number of degrees of freedom of optical control that we have in the quantum computer. So one of the teams that we have at QuEra Computing works on integrated photonic circuits, and they have worked together with Sandia National Labs in silicon nitride, active silicon nitride context to be able to make integrated photonic chips that we can actually scale the control of turning on and off light beams to deliver light pulses to the atoms to control their internal states. And so, the technology stack looks a little bit like what you're seeing on the screen right now. You can see that there's some silicon nitride as a wave guiding material. There's also some aluminum nitride there to introduce piezoelectric or stress optic effect to actually perform the modulation. So we built chips of this type. In fact, we can target a pretty wide range of wavelengths, even all the way down to short wavelengths on the kind of 400 nanometer scale, all the way up into the micron or so. Good power handling, good on-off contrast, all of those types of things, and good modulation speeds of in the range of 10 to 100 megahertz as well. So you're seeing one of those chips kind of flash in real time here up in the right-hand side of the screen. This is actually an array of Mach-Zehnder interferometers that are turning on and off the light, and you're seeing it switch on the right there. So just to give you a sense, 400 to 400 nanometer to about a micron or so wavelengths, we can handle about 100 milliwatt of power. World record contrast in the visible spectrum here, 75 dB of optical isolation on and off ratio, and also 200 nanosecond rise time. So this is a very good tool. It should work for neutral atoms, but it should also work for other systems too, like ions and so forth. And with that, just, these are things that we do work with other companies on quite a bit. So please feel free to contact us, discuss a wide range of collaboration opportunities. If these optical switches might work for your qubits as well, feel free to give us a call and we'd love to talk about it.